Welcome back. This is part 2 of parametric and non-parametric tests of independence. In part 1, we worked through 2 different ways of testing whether the correlation between 2 numeric variables is real or whether it's just chance. In this video, we ask that same question of a completely different kind of data that isn't numeric at all. By the end of it, you'll be able to take 2 sets of categories, lay them out in a table, and test whether they are related to one another. Before we start, one line of recap, because it matters more here than it might seem. In part 1, every test had the same null hypothesis. There is no relationship. That does not change in this video. The data changes completely and the arithmetic changes completely. But the null hypothesis says exactly what it said before. These 2 classifications are independent of one another. So let's look at the kind of data we're dealing with here. Everything in part 1 needed 2 columns of numbers, but a great deal of what analysts classify isn't numeric at all. Value, growth or blend, investment grade or high yield, North America, Europe, or Asia Pacific. There is no such thing as the average of growth, so correlation has nothing to work with here. So instead of measuring, you count. Take 600 equity funds and sort them 2 ways at once, by region and by whether they use leverage. Every fund lands in exactly one of 6 boxes. That grid is what the curriculum calls a contingency table, and the numbers around the edge are the row and column totals. The question is whether those 2 classifications are related. Does knowing a fund's region tell you anything about whether it uses leverage? The null is that they're independent. The alternative is that they're related. Same null as always in categorical clothing. The way this test works is worth explaining carefully, because once you can see the idea, everything that follows it is just arithmetic. We build the table we would have expected to see if the 2 classifications really were independent of one another. Then we measure how far the real table sits away from that imaginary one. If the 2 are close, independence is believable. If they're far apart, it isn't. And you don't memorize how to build it, you derive it from probability. If 2 things are independent, the probability of both is the probability of one times the probability of the other. 40% of these funds use leverage. Half of them are North American. So under independence, 20% should be both. 20% of 600 is 120. Cancel the terms and you get the shortcut. Row total times column total divided by the overall total. Do that for all 6 cells and the expected table drops out cleanly. 120, 80, and 40 across the top. 180, 120, and 60 across the bottom. Notice, they still add to exactly the same row and column totals as the real data. That's the point. Only the split inside has changed. Now look at Asia Pacific and leverage. Independence predicts 40 funds. There are actually 50. 10 more than expected in a cell that only expected 40. That single cell does a lot of the work in this test. And in a moment, we'll say exactly how much. The statistic turns those 6 gaps into one number. For each cell, take observed minus expected, square it, and divide by the expected count. Then add the 6 results up. That total is chi-square distributed, and it's the second formula in this video worth a flashcard. 2 details in that formula do real work. The squaring means a shortfall and an overshoot count the same. A cell 10 under contributes exactly what a cell 10 over does, and dividing by the expected count makes it fair. Being 10 out when you expected 40 is a serious miss. Being 10 out when you expected 400 is nothing. Here's every cell's contribution. Asia Pacific leverage is the largest at 2.5. North American leverage is next at 1.875. Europe barely moves the needle. The 6 contributions add up to 7.81. Degrees of freedom next. And here's the picture that makes the rule obvious rather than memorized. Fix all the row and column totals. Now try to fill the table in. You can choose the first cell freely, you can choose the second freely. After that, every remaining cell is forced. The totals finish the job for you. 2 free cells, 2 degrees of freedom. And the general rule falls straight out of that picture. Rows minus 1 times columns minus 1. 2 rows and 3 columns gives 1 times 2, which is 2. Not the number of cells and not rows times columns. There is one more structural point to make about this test, and it comes up in exam questions regularly. Because every gap between observed and expected gets squared, no departure from independence can ever push the statistic downward. The smallest value it can take is 0, which would mean observed, matched, expected exactly in every single cell. So this test has one rejection region on the right-hand side, regardless of what the alternative hypothesis says. With 2 degrees of freedom, at 5%, the critical chi-square value is 5.991. Our statistic is 7.81. That's past it. Reject the null of independence. The evidence is sufficient to say region and leverage use are related for these 600 funds. Though notice how much the significance level is doing. At 1%, the critical value would be 9.21, and 7.81 falls short of that. Same data, same statistic, conclusion flipped. That's the type 1 versus type 2 trade-off from 2 videos ago showing up live. One last piece, and it turns a test result into something an analyst can use. Rejecting the null tells you something is going on. It doesn't tell you what. For that, look at each cell's standardized residual, observed minus expected, divided by the square root of expected. Positive means more than expected. Negative means fewer. Here, leveraged Asia-Pacific funds come in at positive 1.58, and leveraged North American funds at negative 1.37. So the story isn't just that these are related. It's that leverage is concentrated in Asia-Pacific and thin in North America, relative to what independence predicts. Test yourself before you keep watching. An analyst classifies firms 4 ways by credit rating and 3 ways by sector. How many degrees of freedom does the chi-square test of independence have? And which tail is the rejection region in? Pause here. 6 degrees of freedom and the right tail. 4 minus 1 is 3. 3 minus 1 is 2. 3 times 2 is 6. And it's always the right tail because squared differences can only add. If you answered 12, you multiplied the categories instead of subtracting 1 from each first. That's the distractor this question is built around. Let's finish with the 5 things worth carrying into the exam across both videos. First, which test goes with which data? 2 numeric variables that behave themselves. The test on the correlation, 2 numeric variables that don't. Spearman on the ranks, 2 sets of categories, chi-square on a contingency table. Second, across the 2 videos, there are 2 formulas that belong on flashcards and nothing else does. The correlation T statistic and the chi-square sum of observed minus expected squared over expected. Third, the 2 degrees of freedom rules that get confused with each other. N minus 2 for a correlation because there are 2 variables. Rows minus 1 times columns minus 1 for a contingency table because that's how many cells you choose before the totals decide the rest. Fourth, the chi-square test of independence has one rejection region on the right always. And fifth, sample size drives the correlation test hard. Small samples hide real relationships. Very large samples make trivial ones look significant. Neither is a flaw in the test. Reading the result without reading the sample size is the mistake. And that completes the reading. Across the two videos, you now have 3 tests for one underlying question. Is there a relationship here, or is there not? A test on a correlation when the data is well behaved. Spearman on the ranks when it isn't. And chi-square on a contingency table when the data is categories rather than numbers. Next, in quantitative methods, simple linear regression, where instead of asking whether a relationship exists, we start putting a number on it.